In this problem, we're going to analyze a gun recoil mechanism. In this system, we are going to be designing a spring mass damper system that's going to absorb the shock of firing a projectile from a ground-based or maybe a tank-based system. Here, we're going to fire a projectile which is going to impart what turns out to be an impulse into our recoil mechanism. We're trying to design this such that it is going to have a critical damping factor. We desire this critically damped system so that we don't have overshoot in the recoil. If it overshot, it's going to come back to its original position, overshoot it, and hit the end of the mechanism. Something like a critically damped or an overdamped system is going to asymptotically approach back to its original position. And we desire a critically damped rather than an overdamped system to achieve this, because the critically damped system is going to return fastest to its equilibrium position compared to the overdamped system, meaning that the gun is going to be ready to fire again quicker than in an overdamped system. So there's a couple of things we need to design here. We want to find the damping coefficient that is going to cause the system to be critically damped. So we're trying to find in part A, C. So here we want to find the C of our system. Then in part B, initial recoil velocity of the gun, we're trying to find here what is x dot naught. And then part C, the time it takes to return to a position 0.1 meters from its initial position. So presumably in this problem, maybe it has to return within 0.1 meters before we're able to fire this again, if we're interested in being able to fire this as quickly as possible. All right, so let's start looking at the model of our system here. So we're going to be treating this as an autonomous system where we're going to start the timer right after we fire that projectile, and we've imparted an impulse into our system. Now later, when we look at general forcing, we can actually model this as a forced system where we start the timer and then we can apply an impulse into our system, and we're going to see the same behavior. The difference is going to be, are we starting the time right before the impulse or right after the impulse? So here, we're starting it right after the impulse. So we're going to have this mass, and it's going to be connected to a spring and a damper. The spring, we're given its value, and C, we are trying to find here. And we're going to define X as the position, the horizontal position of this mass here. So what happens is when we fire it, the mass is going to move to the right, and then it's going to come back to its original position. And then we're ready to fire it again. So it's absorbing the impulse of firing that projectile rather than that impulse going into the tank or whatever this gun barrel is directly connected to. So we have a simple spring mass damper system here, and we're given some of the values. So the mass of the recoil mechanism is really heavy. We have a 500 kilogram mass that's going to be moving here. And we're assuming we're given the stiffness of the spring it's connected to, 10 kilonewtons per meter or 10,000 newtons per meter. Again, I want to work in base units for everything I do here, so it's just easier to keep track of. So we want to know the C that is going to be necessary. So at the moment in our model, we don't know what C is. But because we have a simple spring mass damper system, we can at least write most of our equation in motion since we know some of the values. We know that it's going to be 500 x double dot plus cx dot plus 10,000 x equals 0. Again, we're going to be analyzing it right after the projectile is fired, so that mass will have some initial velocity and position, and that's how the system is going to be moving. I'll write the identify step here, and then we'll kind of go back and forth on this one a little bit more. So it's going to be 1 degree of freedom, it's going to be damped, and by design, it's going to be critically damped. So we have critical damping here. And again, we are going to model this as free vibrations instead of including the impulse, which we'll be able to do later in general forcing. So knowing the type of system we'll have, I might as well right now write the closed form solution, and we'll fill in details as we get them later. So it will be x naught plus x naught dot plus omega n x naught times t times e raised to the negative omega n t power. All right, so I'm using again that exp, but that's e raised to the negative omega n t. So that will be the general solution here. Now, some of these things we don't know yet, but we're going to come back when we are ready to assemble our closed form solution. All right, so let's look at some parameters of our system, what we know, what we don't know. With every 1 degree of freedom system, again, it's a good idea, start with the natural frequency. We're going to need it for something. And actually here, we're given enough information to calculate the natural frequency. We're told that the spring constant in this simple spring mass damper is 10,000, and the mass is 500 kilograms, which means that this system should have a natural frequency of 4.47 radians per second. Right, so that's just based on given information. It's a damped system, so you can bet that we're going to want to know the damping ratio. And we know that that is going to be calculated by C over 2m omega n. Now this is where our design comes into play. We desire this to be critically damped. And when we plot the response, again, we're going to see what that looks like. So if we want it to be critically damped, that means the damping ratio must be 1. C we do not know. 2 times, again, 500 is the mass of the recoil mechanism. And we now know what the natural frequency is. So this means that C, for this to be critically damped, that damping coefficient in our system, the damper that we install, must have a C value equal to 4.47 thousand Newton seconds per meter. So that actually is our answer already to part A. That's the C value we're going to need to ensure that using the given mass and the given spring constant, that this gives us a critically damped system. So part A, we have answered. We know the critical damping coefficient. Now, we want to know the initial recoil velocity of the gun. And there's some information here that we didn't use yet. So we have used the 500 kilograms that we've included. We've included the stiffness. We didn't yet use this 0.4 meters. So we're going to fire this. The mass is initially at 0. It's going to travel a maximum of 0.4 meters, and then it's going to come back to its equilibrium position. So we already know that by the design of this, that it has 0.4 meters of travel. So we want to see how fast is the initial velocity of the recoil mechanism if this is indeed the case. So this is more kind of an as-built evaluation of it. We know the M, we put in this C, we put in this spring with a K in it, we fired it, and we see that travels a maximum of 0.4 meters. So we want to know what was its initial velocity. All right, so here we can use some of our parameters we just discovered here. Now we can fill in and discover some of our initial conditions. One of them we clearly don't know is x naught dot. In fact, that's what we're trying to discover in this part of the problem. But the other initial condition we actually do know, x naught is 0. This is going to start at rest. The recoil mechanism starts at its equilibrium position. Then we impart this initial velocity to it from the impulse, and then it starts to move. So we can go to our assemble step, knowing that since we're starting at the equilibrium position, at least, with some initial velocity, we know the value of x naught. So some of the details for x of t we can now fill in, now that we know some of the parameters and at least the initial position. So remember, in general, this was going to be x naught plus x naught dot, which we don't know, plus omega n x naught, times t, times e to the negative omega n t power. All right, so again, based on our initial conditions, we know this is 0 and this is 0. So this will simplify down to x naught t e to the negative omega n t power, in this case because we have an initial position of 0. Now we can use that other piece of information that we were given in the problem. The maximum value that x takes is that 0.4 meters. Right? Again, from measurements of observing it after we fire our system. If we know the maximum value of x and we know the function for x, we're going to be able to relate those two because we know that the maximum of a function occurs when the derivative of our function is equal to 0. So I have our x of t. We can differentiate that and get our x dot of t. Right, so we can take this above expression here and differentiate with respect to time. X naught dot is a constant. That is just the initial velocity. We're trying to find the velocity as a function of t. So we see here we have a function of t times another function of t. We are going to need to use product rule. So it's going to be the derivative of the first times the second. So the derivative of t is just 1. So that's leaving us with e to the negative omega n t plus the derivative of the second plus times the first. Right, so we have to use chain rule. The derivative of e to the negative omega n t is going to be negative omega n. We'll have x naught in front and t, e to the negative omega n t. So this is the velocity, which is the time differential of our position. So again, we know that the maximum position is 0.4. So what we can find is, when does that occur? When does the maximum occur? Well, it occurs when the velocity drops to 0. So when x dot of t, I'll call it t star, equals 0. So it's not when the time is 0, it's when the velocity is 0, is when this maximum position is going to occur. I'll take the above expression, I want to simplify it a little bit. I can factor out an x naught dot, and I can factor out this e to the negative omega n t from it. So I'll be left with a 1 minus, and I'm left here with an omega n times t. All right, so I can simplify this. So 1, I have a 0 on the left-hand side. I have an x naught dot on the right-hand side. I can divide through by x naught dot because it's not going to be 0. Because if the initial velocity were 0, this would not be an interesting problem. Nothing would be happening. So I can safely divide through by that because that will never be 0. Also, I can divide through this exponential term because there is no value of t that will make that exponential 0. Even as t goes to infinity, it approaches 0, but it will never be exactly 0. So I can actually safely divide through by the exponential as well. Which means that this is, I'll switch the sides here, this expression is going to simplify down to 1 minus omega n, which we determined before was 4.47, times t equals 0. And really I'm doing t star here, the time when the maximum occurs, so that we can solve for it. So it's actually only one unknown here, and I can solve for t star. So solving this for my one unknown, t star is 0.224 seconds. So again, what did I just solve? I solved for the time when my velocity was 0. And when the velocity is 0, that means I'm at an extreme point of my position, since velocity is the derivative, the time derivative of position. So what do I know? I know that my position at this time, t star that I just found, was or is 0.4 meters, because I measured that was the maximum position that this recoil mechanism took. And I know from my x of t that that is going to be my x naught dot, which I don't know yet, times t, well t here is t star, so 0.224, times e raised to the negative 4.47 times t star. So the only thing I don't know in this expression now is my value of x naught dot. So I can solve for it. I can solve for what that initial velocity must be for that to be the maximum position that I achieve. So solving this, x naught dot is 4.86. And I'm in base units, so meters per second. So again, just to recap, I know what the position equation must be because I have this critically damped system. I'm able to take the time differential of it, so I know the velocity at all points in time. And I know that when the velocity is 0, my position is at an extreme point, in this case, a maximum value. So I could solve for the time when the velocity reached 0, and then put that time back into my position equation, so I knew the position at the time when the velocity reached 0, which again is the time when I achieve my maximum position, which I was told was 0.4. Then I can solve for what the initial velocity must be in order for the maximum position to be 0.4 meters. And it turns out 4.86 meters per second. So that was part B, the initial recoil velocity of the gun. Now, I want to know the time it takes for the gun to return to a position of 0.1 meters after it's fired from its initial position. Right, so now I actually can fill in the rest of my equation here for x of t, because now I know all of the details of it. Now that I know my x naught dot. So my x of t must be equal to my x naught dot of 4.86 that I just discovered times t times e to the negative 4.47, that's the natural frequency, times t. So I want to know the time when it returns to a value of 0.1. So I want to find t, I'll call it tr for time return. When does this position equal 0.1? And that's equal to 4.86 times t times e to the negative 4.47 t. So I want the t that makes this true, or this is really tr at this point. So I want to find the time it takes to return to 0.1 meters. So my left-hand side is 0.1, 4.86 tr times e to the negative 4.47 tr. I need to solve this for tr. Well, this is going to be difficult to solve algebraically because I have an unknown times an exponential raised to that unknown power. So solving this by hand is not going to be feasible or easily done using, again, by hand, by algebraic methods. So what I'm going to do instead is I'm going to take this and solve it numerically. And I'll solve it numerically using MATLAB. So I can put in my code here. So I'm just reproducing some of the things I just did in the sheet by hand here. So I have my expression for x, and I have all of the other relevant entries in here that I discovered along the way. So first, I can plot x of t. So at least graphically, I can see what's going on, but I do want a more precise solution. But let's see what this is doing. So this does have that initial position of 0 when it's fired. And we can see what happens as time goes on. It's going to reach that maximum x value of 0.4. Well, that's by design. We knew it should be 0.4. We were told it was 0.4. And by discovering what the initial velocity was, we ensured that the maximum it went to was 0.4. And notice this happens at about 0.229 seconds. And that's pretty close, just a little bit off from what we found for that t star, the time when we hit our maximum. So all of this is baked into the plot because we already did this in the equation. And then what happens, it goes to its maximum value, and then its x value is decreasing as it comes back towards equilibrium. And what we see is it's asymptotically approaching 0. There's not overshoot. It is slowly going back to its equilibrium point at 0. And that's a hallmark of this being critically damped, or really it not being underdamped. If this were an overdamped system, then we would see that it would more slowly asymptotically get towards 0, but that's why we want it to be critically damped, so that we would return as quickly as possible without having overshoot. So again, what are we trying to find here? We want to know at what time we are going to return to a value of 0.1. Well, let's see what happens here though. When time begins, it's going to cross 0.1 from below to above at this time, and then it goes to its maximum, and that's going to return. So we actually want this second point here, which we can see graphically is going to be around 0.82 seconds. But let's see how we can actually find this numerically instead of relying on the plot. So what we can do is use this fzero function. So let me show you how the fzero function is working. What fzero is going to do is it's going to find the zero of a function, as the name implies. However, whatever we put into fzero, we're really only putting in one side of an equation. So we are putting in some function, and it's assuming that function is equal to 0. And it's going to find what are the values that make f equal to 0. But the problem we have here in the 0 we're trying to find, or the roots we're trying to find, is that our one side is 0.1, and the other side is the 4.86 tr e to the negative 4.47 tr. So it's not in a format that fzero wants, because again, one side is not 0. Well, that's easy enough to fix though. We can just take the left-hand side and move it over to the other side. So I'll rewrite this. I'll also switch sides here. And now I'll subtract 0.1, and now that is equal to 0. So this expression is what I can put into fzero, and it's going to tell me the TRs, the value of TR that makes this left-hand side equal to 0. So it's going to keep trying different values of TR until the thing in green equals 0. Well, if the thing in green equals 0, that means that our original expression must equal 0.1, because that means when we find the right TR, we're going to get 0.1 minus 0.1 equals 0, and that's going to evaluate to true. So to use fzero to find a root, we just have to make sure we rearrange it such that one side of our equation is going to be 0. So here we just had to modify it and move the 0.1 to the other side. So that's what I'm doing here. So in 72, I'm defining my function, my x of t. Right? So now at that point, I know my initial position was 0. I put my initial velocity, etc. So I have my expression for x. How I'm using it now in 80 is I'm taking that position and subtracting 0.1. So I want to know with this at t, find me the value of t that makes x of t minus 1 minus 0.1 equal to 0. And then we have to give it some initial guess. So if you haven't used fzero in a while, make sure you look in the help in the documentation for what it's looking for. So we have to tell it what variable to keep trying different values of, in this case t, then the function here that we want to equal 0, so it's our position minus 0.1. That way the position will equal 0.1 when this expression is 0, and then our initial guess as to the value of t that would make that true. So let's just see quickly what happens here. If I give it a small guess, let me guess that a value of 0.05 will make this expression 0. And run this. It comes up with a t2 value, so I'm calling it t2 in this case. It's coming up with a value of 0.0228 seconds, makes that expression true. Well, let's see what happens. What value did that actually find? So again, let's just refresh ourselves, 0.0228. That found the first time, basically, that it crossed that 0.1. But we are looking for how long it takes to return. So we actually want this value, that the time that it takes to come back across the 0.1. So the thing about using fzero is that when there's multiple solutions like we have here, there's 2 times this is true. We have found the first time it's true by making this small guess. oftentimes it's going to find the root closest to where your initial guess is. Not always, but oftentimes. So we know that this is not the right one. We need to try a different value to find the time where it crosses the second time. So if I put in 0.4, notice it gave me back that same result. And again, I know that is not correct. We try an even bigger guess of 0.9. Now, I ran the same code again, but just with a bigger guess, and it found 0.8255. And that looks to be about right based on the graphical solution we have here. So that's the time for it to return to within 0.1 of its equilibrium position. So it's sensitive to that initial guess that we give it, so 0.8255 seconds. So solving this numerically, we found the time to return to within 0.1 to return to 0.1 was 0.825 about seconds. So we could not solve this one by hand. We did use a numeric method. We used fzero to do it, and we just had to be aware there were actually two solutions, but the first one was not correct. That's how long it took to pass 0.1 the first time. It took 0.825 seconds for it to come back to being within that 0.1 meters.